What's up, party people? So this is the video for exercise 5. In this one, we'll be covering the test called an ANOVA, which is basically, if you remember from literally the last one, we did a t-test. The only difference between a t-test and an ANOVA is that it's more than 2 groups. I can't remember... I should have checked this before I hit record, but I'm not sure if it was this book or a different textbook. But I've seen some books define an ANOVA that it needs 2 or more groups, but it needs more than 2 groups, so a minimum of 3 in order to run an ANOVA. And it's basically the same thing. You're looking at the mean difference between multiple groups, except instead of just 2, now you can have more than 2. Before I get started, I just wanted to point out right up here, this does use a different file. So you can see right here, it is highlighted in orange. Since it has been a minute, I just wanted to download that with you guys. So, if you forgot, if you go to files, you can see right here, files, and then SPSS, data, and then here's any conceivable file that you might need. So we need the 14A. You'll just hit download. And obviously, if you are working on the remote version, you'll have to go through all of those steps to get it onto your OneDrive. Whatever you did, the previous file with the 2021 file, you will go through those same steps. So that is downloaded. What if I hit the right program? And, you'll just open it. You can open it from your desktop or whatever, whatever floats your boat. So we've got data. We've got our assignment here. Okay. And I need to zoom in. Let's just do that. Okay. Hey, that's great. All right. So exactly the same thing as your previous exercise. I've given you kind of a scenario here. I'm asking you to look at if there is a difference in the average age of people and how they feel about premarital sex. So that was a question on the GSS. You again have an alpha of 0.05. Just to reiterate, you will never pretty much not use a minimum of 0.05 to kind of check your p-value against. And I've also given you, again, the variables right here. So you have age and then pre-mar-sex, however you might pronounce that. So ANOVA has 2 different ways that you can kind of run it. I'm going to show you both ways, and then you can do whichever one, whichever one you prefer. It doesn't matter to me, live your truth. So first one, we'll go to analyze once again, and then there's general linear model, and then you're going to do univariate, which basically just means you only have one. You're testing one variable on one other variable. We don't have you're not doing a multiple you won't have multiple independent variables or anything like that. So univariate 1, uni 1. Okay. So once again, you can just display variable names. If you want to, you can also hit sort alphabetically, but they're already in alphabetical order, so you don't have to worry about that. In this dependent variable box, which is the very, very first one, that's where you're going to put age, since that's our first sort of variable here. The dependent variable box is where you will always drop the continuous variable. So, bam, done. Next one that we're looking for is the premarital sex one. So that's in fixed factors. Now, this, for the first time, you do need to do some stuff in the side here. You can still mostly ignore them, but you'll need to go to options here. And to make sure that it kind of produces all of the numbers that you need. you'll want to turn on this descriptive statistics, and then you can just leave the rest of it alone. These are for like checking if your variables are like too related to one another, things like that. Just if you're wondering what heteroscedasticity it even is. So that means that they're too related, they're explaining one another. So obviously they will probably usually come out significant, and it would throw off your results. Again, we're not doing that in this class, but just so you know that it is a thing, that it exists. So you'll hit continue. And that's it. That's all. The only thing you have to do. Options, descriptives, literally ignore everything else. And that's it. Then you'll hit okay. And now you get some tables. Yay. So this one is just frequencies. You can ignore that. What you do need is this descriptive statistics box, which will not be there unless you check that box. And then you'll have this test of between subject effects. So let's go back over to our assignment here. Same thing here as in exercise 4, except now I'm asking you to also include a research hypothesis. This is also called an alternative hypothesis. It's basically the opposite of a null. So you'll remember the null is a statement of no difference. A research hypothesis is you're saying, okay, this is what I think is happening. Again, in practice, these are normally very specific. You'll say, I think that this particular variable specifically is going to increase, I don't know, for example, CO2 emissions. I think that the lack of a democratic government within a country increases the amount of CO2 emissions that a country will have. That would be, for example, a research hypothesis, except worded better than that, a little bit more eloquently. I just want you to practice kind of, again, the wording, the kind of precise wording, and also understanding the difference. So with the null hypothesis, it's going to be, surprise, surprise, the exact same as your previous assignment. You'll say there is no significant the mean age of individuals based on their feelings about marital sex. Wow. Okay. I almost got through without any typos, which is pretty good considering I'm typing around a microphone and a cat. So you have all of that done. Literally the only difference between your null and your research hypothesis will be, actually, let's go here. There is a significant difference in the mean age of individuals based on their feelings about premarital sex. Wow. That is literally the only difference between these two statements. You can also, I forgot to mention this in the exercise 4 video, but you can write these mathematically as well. Personally, I think a sentence is a lot easier. And it's easier to communicate to people who maybe don't know stats, right? I will take either. And here you could put a whole number of things. You would just say, like mean, it would have the mu, the little u. It would be the mu 1, 2, 3, and 4, and they would be all not equal. The equal sign would have the slash through them. That's it. That's what the research hypothesis would be for this. Okay, so, excuse me. Again, just like we did with the t-test, you'll go through and you'll look at the mean for each of these groups. So we have our descriptives box right here. So the average age of people who said that premarital sex is always wrong was 54.25. Remember, two decimal places is more than enough. But please do include 2 decimal places at least. And then almost always wrong, we have 52.12. Sometimes wrong is 53.18. And then not wrong at all is 47.37. And this is all years, obviously. And you can type that in all of these, I guess, if you wanted. Well, I can't even type the word years. I'm killing it today. Okay. So then our next table is going to be, again, our actual test. And that will come from, excuse me, this third table. You have to kind of look at a couple of different rows here. But it's pretty much going to be the same as a t-test. So very, very first thing I want to look at is your F statistic. We know that we are testing the variable premarital sex. So whatever variable your grouping variable is, that's the row that you're going to look for. So right here, boop, and then this row. This is our F statistic right here. The F statistic is, well, it's the F ratio. Is basically serves the exact same function as the T statistic from t-tests. It is just like the kind of older, like version of like how you would check to see if this test was significant or not. So now we've got our nice little mathy number here where, and that's taken care of. The next thing is, you'll see there's 2 different DFs, degrees of freedom. There's DFB, which is degrees of freedom between. And then there's DFW, which is degrees of freedom within Dallas-Fort Worth. Degrees of freedom between is going to come, again, from this same... from this same row. There we go. Thanks for moving, yellow box. And it's going to be 3. Why is it 3? Degrees of freedom between, again, is degrees of freedom between groups. So the way that you would calculate this, if you're, again, not sure which number you should be pulling, is the number of groups that you have minus 1. So we have 4 groups, 1, 2, 3, 4. Minus 1 is 3. Who would have thought? That's usually denoted by K minus 1. K is, I guess, for categories. And imagine that word cooperates. So 3. Bam. Easy peasy. Okay, so then the next one is degrees of freedom within. This is calculated by taking the total number of observations that you have minus the number of categories that you have. So it's the other way around. Number of observations minus the number of categories. Is that what I said the first time? Probably. So it's N minus K. Again, these will always be whole numbers. Somehow, some way, someone will pull a decimal out here, and I don't know how, but we have, we have our total here, 978 minus 3 is 975. So you literally pull that from the error column, or row, sorry. 975. Wow. So then the last thing that we need here is our P, which will come again from the same row that whatever your group variable is. So right in here. And you'll always kind of check this significance column. That's generally where your p-value will be. It'll be under sig. And then you need this specific row. So you can see again, it is less than 0.001, which is totally fine if you put that here. And so again, we know that 0.001 is smaller than 0.05. which means that we would reject the null. If that is the case with an ANOVA, you have to do a whole extra step. Because the way that an ANOVA works is it will tell you, okay, yeah, there's a difference between these groups, but it does not tell you where, like which group is significant, because it could just be maybe always wrong and sometimes wrong. But the others are not statistically significant. It will, so you need to figure out where that difference is. You do that by running what's called a post hoc test, which post hoc just means like after the fact, basically. So you'll go back to analyze, and then the same general linear model, univariate, and you'll see this post hoc button. You want it to run on this particular group, and the one that you should run for this is this 2-key one. It's right under SNK. You can see there's a bunch of different ones. They are all for different types of tests, different types of variables. The specific one that you want is this 2-key, which when I was an undergrad, I read it on the projector as my professor was doing it as turkey. And so in my mind, it will always be turkey. You want the turkey test. Okay. Not the turkey's SB. Nope. Not that one. Just turkey. Just plain old turkey. And you'll hit continue, hit OK. It'll rerun everything. But the next table that you need is this one, this multiple comparisons. The easy way to tell, I mean, you can check the significant column for any number, any of this that is less than, again, 0.05, or it puts an asterisk on any of them that are significant. The other thing to keep in mind when you're looking at this is that it gives you every pairing. So you'll have overlap, right? You can see always wrong, almost always wrong. But then here you have it the other way around, almost always wrong and always wrong. So say that this were significant, you wouldn't list that twice. You would just pick one. Usually what I try to do is keep everything with the same sign. So I will say like this is older, so I'll only take the positive numbers versus the negative numbers. So here you can see always wrong and almost always wrong. The people who said always wrong were 2-ish years older than almost always wrong, versus if you reported it the other way around, the people who said almost always wrong were 2-ish years younger than the people who said always wrong. It doesn't matter to me how you do it, but that is my general rule of thumb. And again, I think that it helps with like not accessibility, but like readability. It makes more sense to anybody that will be reading your work. So I would say just pick one. If you want to go all positives, do that. If you want to go all negatives, do that. Okay, so we have our thing here. You would say, I reject the null hypothesis. RP is, less than 0.05. There is a significant difference in the mean age of individuals, their feelings on marital sex. And you don't put 2 spaces between that. Why are you telling me? Did I spell marital wrong? I must have spelled marital wrong. Okay. So, if you are rejecting the null, if there is a significant difference, then you have to report the results of your post hoc test. So you have to run that. The next part that you would do, instead of just stopping there, you would say on average, those who said sex before marriage was always wrong were 6.88 years older than those who said it was not wrong at all. And then where's our next one? And those who who said it was sometimes wrong were 5.82 years older than who said it was not wrong at all. Okay, so we hit both differences, right? These are the exact same pairs we have, because we have always wrong and then sometimes wrong and not wrong at all. So these are the same pairs. We already hit both of them. That's it. That's the end. This is, again, this is all you would need to do. Excuse me. Something that I would, I guess, caution you against is I've seen people just run the post hoc test anyway, but then they end up reporting numbers from the wrong table. So, until you're like, you really know what you're doing, I wouldn't just run a table, unless you know you need it, because it's harder to sift through all of this stuff when you're like less familiar with what you're looking at. So this is method 1 for how to run an ANOVA. I will show you the other way, and you can do it again. You can choose however you want to do it. I'm actually just going to close this so we can start with a new output window. So you can go to Analyze and then Compare Means, and we're going to do a one-way ANOVA. Wow, who would have thought? So we need age up here, and then pre-mare sex goes in that factor options. You do want to turn on descriptives. Again, it will not have that table otherwise, and you won't be able to pull this information right here for each of the groups. So you'll hit continue and you hit OK. You have your descriptives. That's all in the same table. And then the next table you have is the ANOVA table. You can see here, it's pretty similar to the other one, probably a little less busy, but you have between groups, which will give you your degrees of freedom between. You'll also get your F ratio from there, as well as your significance. So you can see those numbers they all match. And then you have the within groups row, which will give you your degrees of freedom within. Literally, they're all the same. Again, since this was significant, you would need to run the post hoc test. So this, I don't know why this particular post hoc dialog box is slightly different, but you do the exact same thing. You just turn on this, the turkey test, hit continue, it'll rerun it. You get that same multiple comparisons table. You go from there. I'm fine with either version. I think that this one's probably a little bit easier to read, honestly. But the other one is better for, again, if you pursued this in any way, and you would need more information than what this particular one gives you. So they both have their strengths and weaknesses. Doesn't matter to me which one you do. So that is the very, very first one. Your second one, you will again do on your own. You will see the awesome little red asterisk here, and you'll need to recode. So please, you'll do that on your own as well. And whichever method you feel inspired by, feel free to use. As always, email me if you have any questions. Other than that, good luck, have fun. I don't know. Okay, bye.